Hello everyone, my name is Brian. The purpose of this video is to explain how to apply the stochastic Frandia model in STATA. So first I'm going to explain to you what the stochastic Frandia model is all about before we go to the practical demonstrations. So before we explain what a stochastic Frandia analysis, we must start by appreciating the concept of a production frontier. The reason is that the stochastic frontier model is an extension of the conventional production function approach. So in a conventional production function approach, we simply estimate our output, which is normally production or value added, real value added, against conventional factors of production such as labor and capital. And then we would add an error term from that specification in that specification. Now, the assumptions that we made in such a production function is that we typically assume that all the producers in the sample, that is if we are relying on cross-sectional data, so we'll be making an assumption that all the producers in our sample are fully efficient, that is they operate along the production possibility frontier, and any deviation from that production possibility frontier is only due to random shocks. That's why we just add an error term. But this is not the case when we have a situation in which the deviation from that production possibility frontier comprises two parts. The first part being the random shock component and the other one being technical inefficiency. Okay, so now this later explanation is what we call the stochastic frontier analysis, and it was proposed initially by Enya et al. 1977. So as you can see from this specification here, this is a typical stochastic frontier model. That's how it typically looks like. So you can see that we have our output in logarithms, we have labor, we have capital. I'll talk about this T is just a time trend, which we normally include to capture the possibility of technical changes. And that is if we are dealing with either time series or panel data. And then this would be, so this here, what you see in parentheses, is our composite error term. So you can see that the composite error term comprises two parts here. The first part, the VIT, is that element which accommodates random shocks. So it's the normal disturbance term, which has a mean of 0 and a constant variance. So it should be homoscedastic and should be normally distributed. And then the second component here, which is UIT, is the technical inefficiency component. So as you can see that this is an extension, this is simply an extension of the classical production function, in the sense that it tells us that from this part up to this part we have output that is explained by labor, capital and a trend component, but we can also deviate from this production possibility frontier due to UIT, which is technical inefficiency. So what the stochastic frontier analysis would then do is to compute this technical inefficiency level and then proceed to the next step, which is this step where you or we might be interested in analyzing or establishing factors that determine technical inefficiency. So this could be farmers, this could be industries. So we might be interested in understanding what really are the factors that are causing these industries to be technically inefficient. So we can compute that with this data, and we'll be doing that in a moment. Now, measuring technical efficiency requires first an appreciation of what the definition of technical efficiency is. So by technical efficiency, we are simply talking of the ratio between actual output against potential output. So if we have a cross-sectional data set in which we have, let's say, 50 farmers, so the best production frontier, the best practice is going to be computed from those 50, and then any deviation from that best practice will be termed technical inefficiency. Okay, now technical efficiency comes in two key forms, and it's important for us to appreciate these two types of technical efficiency. The first one is called input-oriented technical efficiency. Okay, so the first one is input-oriented technical efficiency, and the other one is output-oriented technical efficiency. Now, input-oriented technical efficiency is that type of an efficiency where we need to establish how possible it is to change our input levels, that is the input vector, holding our output constant. So in other words, we are trying to quantify the extent to which we can reduce our inputs that we are using, which is labor and capital, without changing our level of output. So we are assuming that we are holding output constant, and we want to check the extent to which we are able to reduce the amount of inputs that we are using in our production. Then the vice versa is true for output-oriented technical efficiency. So in this case, the objective here is to hold our inputs constant and then try to establish how possible it is to increase our output. So we want to quantify the extent to which it is possible to increase our output without necessarily having to change our inputs, or that is to increase our inputs or reducing them. If we hold them constant, we want to determine how it is possible to increase our output. And if it is in a time series framework, we might also be interested in holding as well technological progress constant and see how it is possible to increase output. Now, there's a graph here that I intend to explain to you these two concepts. Now, so what we see here on the axis is the input x. So this could be labor or capital. And then here on the y-axis we have our output. So this would be the production function here. This would be the production function. Now, anything. So you see, these are then the actual output. These dots that you see here. So that if you pick, let's say, this actual output here and compare it with this level of output, which is on the production frontier, maximum production frontier, you see that this whole gap here is technical inefficiency. Okay, so this producer here is operating below the production possibility frontier, and therefore this producer is technically inefficient. But now notice that this producer can be technically efficient in two ways. In other words, this producer has two routes to choose in order to operate at the maximum possibility frontier. One is to move from this point here and move upwards, up until the producer reaches the maximum production frontier. Now, so if this producer reaches this part, you see that we can consider by definition this producer to be technically efficient. But what has happened here is this producer has simply increased output. So output has increased from Q1 up to a certain level of Q, we can say Q2 here at this stage. But notice that we are holding X constant. So if X is our labor or capital, so this producer has managed to use the same level of output to increase output from Q1 to Q2. So the same level of inputs is allowing the same producer to increase his or her output from Q1 to Q2. Now we call this output-oriented technical efficiency, okay, because our inputs are held constant and we have managed to increase our output. Now the other route is to go this direction until the producer is now operating at this production possibility frontier, the maximum best practice. So what has happened here is, if this producer is now at this point, we can consider him or her as technically efficient. Now, but if you check here, this producer has not increased output, but he has managed to reduce the quantity of inputs that he or she has been using from X1 to maybe X0 or X star here at this point. So we can see that at this point there is a significant reduction in the inputs that have been used, but output has been held constant. So this is what we call input-oriented technical efficiency. Now, the choice between input-oriented or output-oriented technical efficiency depends on the situation on the ground. For example, if you are interested in a project in which you feel that the farmers are having a wasteful resource, are wastefully utilizing their resources, so you might be interested in determining how possible it is for those farmers to reduce the use of inputs without changing the level of output. So it depends on the context in which we are doing our stochastic frontier analysis. Okay, so now that we appreciate these two terms, I'm gonna use this data here to explain to you how we can run a stochastic frontier analysis in STATA. Now, before I do that, let me further explain to you some of the key issues that we need to be aware of when we are running this model. The first thing is, when you are looking at these two specifications, you see that this first part here is actually the stochastic frontier model, because it is from which this model that we are going to determine the deviations from the PPF. And then when we compute this one, we are going to go to the second step, where we now need to identify other exogenous factors that affect technical efficiency. So you can see that this analysis can proceed in two steps. The first step is where we estimate the stochastic frontier model, and then we generate from this model our levels of technical efficiency. Then those levels of technical efficiency or technical inefficiency are then used as the dependent variable in the second stage. So it typically follows two steps. But there is a paper by Wang and Wong 2002 or 2000 which identified, in other words, it argued and demonstrated that if we follow this two-step procedure, then we are gonna have biased estimates. There is a persistent bias that is characterized by this two-step procedure. So in order to avoid that bias, they proposed a one-step approach in which you simply simultaneously estimate the stochastic frontier and at the same time incorporate factors that affect technical inefficiency. So this is the approach that I will follow in this demonstration. Another critical thing that needs to be taken into account is the functional form. The functional form of the production possibility frontier. So there are two commonly applied functional forms, namely the Cobb-Douglas production function. The second one is the translog. So the translog is more flexible than the Cobb-Douglas, and the opposite is true for the Cobb-Douglas. It's relatively more restrictive. So the most important thing for you to know is that each of these two functional forms is not without its own limitations. For example, the translog specification is the advantage that it is flexible, but it can create problems when it comes to the issues of curvature. And also it might create you multicollinearity problems, especially when you include polynomial terms and interactions. So sometimes you might, for convenience purpose, estimate a Cobb-Douglas for simplicity. But the Cobb-Douglas again is its own weaknesses, which is that it is too restrictive. So the best practice would be to estimate the Cobb-Douglas and the translog and then make a likelihood ratio test to determine which one is more appropriate. But for the purpose of this video, I'm gonna proceed with the Cobb-Douglas functional form. Now, so I'm using my example using a panel data set on 28 manufacturing industries in South Africa. So these are South Africa's 28 manufacturing industries, and what I intend to establish here is I need to say here this is output, this is capital stock, this is employment. So these three columns are the variables that I need to estimate the production possibility frontier, which is the frontier analysis. And then when I estimate this model, I would need to establish how import penetration or import competition affects technical efficiency of these manufacturing industries. So there's a theory which says that imports can improve technical efficiency of domestic firms by increasing competition. So firms will increase their technical efficiency in order to avoid perishing due to the fierce competition that comes with imports. So I need to check whether this prediction is true, because we also have other arguments in literature which say that imports can displace domestic production. So there is an inconclusion here. It's inconclusive. We don't really know a priori how imports affect technical efficiency of domestic industries. So let's apply this data set and check whether in the South African context between 1970 and 2016 import penetration is correlated negatively or positively with technical efficiency. So I'm copying this data set. So I'm gonna go to my STATA. This is my STATA, and the data set here. Okay, like that. So I've entered here. These are the names of my industries, the year variable, the ID variable, output, capital stock, employment, and import intensity. So by measurement, it's a percentage of output. Okay. So if you check here on the upper right hand side, you find that the list of my variables are now appearing here. So first I'm gonna declare that this data set is panel. Okay. So once I have done that, I am gonna use what is known as the SF command. Okay. So I'm throughout this example, I will use what is known the SF panel command. This one. So this is a command which allows you to estimate different versions of stochastic frontier model in a panel data analysis. If you are interested in doing your stochastic frontier analysis using cross-sectional, then you would need to have SF cross. Okay, so I'm gonna stick with this command. And if you have not yet installed this command in your STATA, you would need to go to the internet and start by typing ssc install sf panel, and then you click enter so that you install this SF panel. Likewise, if you have not yet installed SF cross, you would need to go on the internet and type this ssc install sf cross. So I'm not going to do that because I've already installed this on the internet. Okay. So for demonstration purposes, there are so many versions of stochastic frontier models in panel data. Some are time varying, some are time invariant. The assumptions, so in other words, we have those versions of stochastic frontier models which treat the technical inefficiencies as time invariant, but others treat it as time variant. So you need to look and study in the literature to determine which one would you feel suits your data very well. But for the purpose of this demonstration, I'm going to use green 2005 true fixed effects. Now the true fixed effects by green 2005, it separates time invariant heterogeneity across these industries with time varying technical efficiency. So according to Green, they argue essentially that when you are observing output over time and across several industries, you might deviate from the production possibility frontier due to two things. One could be unobserved time invariant heterogeneity, and another one would be technical inefficiency. So they try to separate this in these true fixed effects. That is why I have chosen it for demonstration purposes. So it's called the true fixed effects model by Green. And another thing that I forgot to explain to you is it's also important to select the distribution of this technical inefficiency component. And there are basically three distributions that we can assume. One is the normal, another one is the half normal, and you also have the truncated normal, we have the gamma. There are so many distributions, but I will assume here the truncated normal distribution. Okay, so the command here is SF. Okay, so before I estimate the this true fixed effects, I first need to transform my variables into logarithms. So to do that, I'm going to type gen log y is equals to log output. So here by this command, I've transformed output in logarithms, and let me also transform labor log L equals to log for capital. There we are. So I'm gonna make use of these variables that have been transformed in logarithms. So the command is sf panel. Then we start with the dependent variable. We proceed with the independent, and because I'm assuming a Cobb-Douglas specification, I am not going to include interactions and polynomial terms. And I'm gonna put here as a trend variable to control for technical changes. Then after here, put a comma. Then we put the name of the model. I'm gonna say TFE because I'm using true fixed effect. So there are other stochastic Flandria models like the Bartesian Coel in 1995. You would need to change the name here if you are using that model. But here I'm using true fixed effects. And then distribution. This is the distribution of the technical inefficiency component. So I'm going to assume that it's truncated, normally distributed. Then next is the E-mean. Now the E-mean here is the model. It's like it specifies that model in which technical inefficiency is affected by other exogenous factors. So here, because I need to check how imports affect technical efficiency of manufacturing industries, I'm going to put where is it, the share of imports on output here is the only exogenous variable. And then ORT for orientation, is it input or output? So I'll put O for to tell STATA that this is output oriented technical efficiency. Once I'm done that, so let me just copy in case you guys cannot please see clearly. This is the command. This is the command in case you can't see clearly. So this is the command that we are using. Okay. So once we have done that, we click enter. and STATA begins computing. And we have so many iterations because we are using the maximum likelihood estimator. So there we are after 100 iterations. This is our output. Now, what this output says is that, let me try to make it bigger. What this output says here is, okay, this is the number of our observations, the number of our groups. Okay, this is the number of industries, and then here the probability is 0, meaning to say that this whole model is significant. And then so this is the Frandia regression model. So the upper part is the Frandia regression model. So log L is our labor, and you can see that the coefficient is in line with economic theory, is positive and significant at 1%. Capital is also positive and significant at 1% level. And our trend variable, which is proxying technological progress, it is significant. It is significant at 1%, which means that during this period there's been positive technological progress. So there's been outward shift of the production possibility frontier. Now, when we go beyond, below this, we have our mu model, which is the technical inefficiency model. Now, it's important for you to know that the dependent variable in this model is technical inefficiency, which means that the negative sign that you see here is actually a positive effect on technical efficiency. I will repeat that again. The dependent variable here is technical inefficiency, meaning to say that if you see a negative sign here, it means that that variable has a positive effect on technical efficiency. Put differently, the negative effect here means that imports have a negative effect on technical inefficiency. So in other words, as we get more and more inputs, we are actually having a situation in which technical inefficiency is being reduced. So in other words, industries in South Africa have become much more efficient owing to imports. This is what the coefficient is saying, and it is significant at 1%. Now, it's important to conduct a number of diagnostic checks to see to validate whether the stochastic Frandia model is the relevant model. The reason being that if we come back here, you can see that if this is statistically not different from 0, then we will see that this entire Cobb-Douglas specification will collapse to a Cobb-Douglas specification if we don't have this. So if this is statistically 0, then our stochastic Frandia model will reduce to a Cobb-Douglas production specification with normal errors. So it's important for us to conduct a number of diagnostic checks. So one way of checking the relevance of the stochastic Frandia analysis is to consider these two statistics, these ones. So we can compute the total variance of our error term. We can categorize it into two parts. One, which is the variance coming from the inefficiency component, and the other one coming from the random component. So that the ratio between the variance of the technical inefficiency component to the total variance of the error term will give us a statistic that accounts for the proportion or the variation in output accounted for by technical inefficiency. And this statistic will range between 0 and 1. If it is close to 1, then it simply means that much variation is being accounted for by technical inefficiencies, and therefore the stochastic Frandia model would be the most appropriate one. And then if this ratio is close to 0, it simply means that very little variation is accounted for by technical inefficiency. So it won't really be reasonable to estimate a stochastic Frandia, because much variation will be simply coming from random random things or random variation. Now, so to do that, here we have our standard deviations which have been computed by STATA. So we can just copy them, or we can say gen, let's say gen var u is equals to, no, let's do this in Excel. I thought there's an easy way of doing that with the STATA, but I don't think we'll succeed. So let me do that in Excel for you. So I've just copied and pasted in Excel. So this is, let me call this var u, and then var v, and then the standard deviation of the random term will be this one. There we are. So this one is the standard deviation of the random term, and this one is the standard deviation of the technical inefficiency term. So the variance would be this squared, and the variance of this squared. So the total variance would be this plus this, which is 0.9. So that the variance of the technical inefficiency would be, so this would be this divided by this, which is 0.3. So what this means here, what this statistic means is that technical inefficiency accounts for about 14% variation in our output. So we can see that it's relatively close to zero, which really does not provide strong justification of the stochastic Frandia model. So we typically we should have this variable close to 1, 0.8 above and above. It will provide pretty much justification for a stochastic Frandia model. But however, according to Kumbaka et al. 2015, they say that this measure is not really advisable to use in order to check the relevance of the stochastic Frandia model. They suggest that we conduct the likelihood ratio test statistic, in which we estimate two models. One is the restricted model. The restricted model is simply a Cobb-Douglas here, so it is not a stochastic Frandia. And then this is an unrestricted model, which is the stochastic Frandia. So when we compute this statistic, we'll compare it with the critical values that are reported in Code and Palm 1986. Okay. Now, so let's do this and see what we'll get. So because already we have this logarithm, this likelihood here for the stochastic Frandia, we are just going to copy this and paste it here. So let's call this for the unrestricted, and then for the restricted one, we'll say GLM for general linear model. Yeah, there we are. So this is the restricted variation. It's not a stochastic Frandia model. So we copy this, we paste it there. There we are. So now this here says that we should compute a statistic of this sort, -2 times the restricted is this one minus this one, which is 530. I hope we did the right thing here. -2 times open bracket, the restricted version is this one, minus this one just to make sure is equals to this one. So it's 530. Now we compare this 530 value with the critical values reported in Code and Palmer 1986. So we have one restriction here related to the variance of the technical inefficiency component, and we can see that with 1 degree of freedom and 1% level of significance, we can see that 530 is above 5.4. So we can reject the null hypothesis, which says that the stochastic frontier model is not appropriate. In other words, we are strongly rejecting the null hypothesis of no technical inefficiencies. So this provides justification of a stochastic frontier model. Okay. So now let's just re-estimate our stochastic frontier model. Okay, so back to our output. Now, now that we have established that there is a positive relationship between imports and technical efficiency, or in other words, there is a negative relationship between imports and technical inefficiency, we might be interested in computing the levels of technical efficiency of these industries during the period. So to do that, we will use the command predict TE for technical efficiency, comma, JLMS. Now this command simply tells the STATA to compute technical efficiency levels from this estimated model using the approach suggested by Jondro et al. Okay, so if we click enter, we can see here on our top right hand side that we now have a variable called technical efficiency, which has been computed automatically on the click of the button. If we go here, we'll see that we now have our technical efficiency levels, which range between 0 and 1. And so they range between 0 and 1. 0 means that the industry is technically inefficient, totally inefficient, and 1 means that the industry is 100% efficient. Okay, so this is our technical efficiency variable for the industries. You can see that it varies over time, and we can summarize this variable by sum TE. Okay, so now we can see that on average, a typical industry in the sample between this period had a technical efficiency level of 0.52, which is 52.3%. Now, if we say 100 minus 52.3, so this is something like about 47%, okay, technical inefficiency. So one way of interpreting this is to say, on average, a typical industry in the sample had a technical efficiency level of 52.3%, which similarly means that on average, a typical industry was operating about 47% below the maximum potential output. So another way of interpreting this mean is to say that during the sampling period, it was possible, there was a possibility that an average industry could increase its output by 47% without having to employ more labor and more capital. So holding labor and capital constant, there was a possibility of increasing output by 47%, about 47%. And then the minimum here is 24. So the least performing industry was performing at a level of 25%, which is about 75% below the maximum potential output. And the best practice industry operated just 1% below the maximum possibility frontier. Okay. So this is it about the stochastic frontier analysis. So you might need to do other statistics like the histogram. You can always do that to characterize firms. You can come here and check and rank these industries according to the level. So you can do that separately to see the average efficiency level of industry A and that of industry B, and then rank accordingly. Thank you very much for your attention. I would like to encourage you to study more, because there are several other models that can be used in the framework of stochastic Frandy analysis. For example, here we have just estimated using the true fixed effects, but we also have the true random effects. So you can try to see which one suits your data. Thank you very much, ladies and gentlemen, for your attention. I'll upload the next video soon.